Imagine the sky splitting open, not with thunder, but with an eerie, silent flash of light during an earthquake. What if these luminous displays, seen for centuries, hold secrets that defy our current understanding of physics? Join us as we unravel the captivating mystery of earthquake lightning, a phenomenon as beautiful as it is baffling. For centuries, eyewitnesses have reported strange, glowing lights dancing in the sky during earthquakes. From the 1965 Matsushiro earthquake swarm in Japan to the 2009 L'Aquila quake in Italy, these fleeting luminous displays, often described as flashes, arcs, or glowing orbs, have sparked wonder and debate. Viral videos from recent quakes like the 2023 Turkey-Syria earthquake show skies illuminated with bursts of blue, white, or even reddish hues, defying the chaos of the trembling earth below. These are not thunderstorms or auroras, but something far more enigmatic. Earthquake lightning or earthquake lights, EQL. The rarity of these events adds to their mystique. They appear unpredictably, often lasting mere seconds, and are reported in only a small fraction of earthquakes worldwide. Yet their beauty, silent, otherworldly glows against a darkened sky, captivates those fortunate enough to witness them. The central question looms: what are these lights, and how can they exist in the midst of geological upheaval? Are they a trick of the eye, a byproduct of seismic forces, or something yet to be fully understood by science? Earthquake lights have been documented for centuries, woven into folklore and early scientific records. In 373 BCE, Greek historian Thucydides described flames in the sky during an earthquake in the Peloponnese. In 1888, accounts from New Zealand's North Canterbury quake spoke of the strange lights flickering over the horizon. These reports span cultures and continents, from 17th century Japan to 19th century California, where miners during the 1906 San Francisco earthquake swore they saw glowing streaks in the sky. These historical anecdotes, while compelling, were often dismissed as superstition or optical illusions. Early scientists lacked the tools to investigate, and skeptics attributed the lights to electrical sparks from damaged power lines or misinterpretations of natural phenomena like lightning or auroras. Yet, as modern technology captured clearer evidence, photographs, videos, and seismic data, the reality of earthquake lights became harder to deny. The 1960s marked a turning point, with systematic studies during Japan's Matsushiro earthquake swarm documenting lights in correlation with seismic activity, reigniting scientific curiosity. What causes earthquake lightning? Despite decades of research, the phenomenon remains elusive, with several competing theories attempting to explain it. Scientists agree that EQL are likely tied to the immense geophysical forces unleashed during an earthquake, but the exact mechanisms are still debated. Here are the leading hypotheses. One prominent theory involves piezoelectricity, the generation of electric charges in certain minerals, like quartz, when subjected to mechanical stress. As tectonic plates grind and shift, quartz-rich rocks in the Earth's crust are compressed, potentially releasing electric currents. These currents could ionize the air, creating visible light or plasma-like discharges. Laboratory experiments have shown that stressed quartz can produce faint glows, but scaling this to the dramatic displays seen in nature remains a challenge. Critics argue that the energy released is too weak to account for large-scale lights visible kilometers away. Another theory points to frictional heating along fault lines. As rocks slide past each other, the intense friction could generate heat and electric charges, leading to triboluminescence, a phenomenon where mechanical stress causes materials to emit light. This could explain localized glows near fault zones, but it struggles to account for lights seen high in the sky or far from the epicenter. Some researchers propose that earthquakes disrupt the Earth's electromagnetic field, creating conditions for luminous phenomena. Fault movements may generate electric currents that interact with the atmosphere, producing plasma or glowing discharges. This theory gained traction after studies of the 1989 Loma Prieta earthquake in California, where unusual electromagnetic signals were detected before and during the quake. These signals could, in theory, ionize gases in the atmosphere, creating aurora-like lights. Another hypothesis suggests that seismic activity releases trapped gases, like methane or radon, from the Earth's crust. These gases could ignite or react chemically in the atmosphere, producing glowing orbs or flashes. This idea aligns with reports of fireballs or glowing clouds during quakes, but direct evidence linking gas emissions to EQL is sparse. A newer theory posits that earthquakes induce charge separation in the atmosphere, similar to processes in thunderstorms. As seismic waves propagate, they may agitate particles in the air, creating electric fields strong enough to produce visible discharges. This could explain why some lights resemble lightning or St. Elmo's fire, a glowing plasma seen in strong electric fields. Each theory has its strengths and flaws, and no single explanation fully accounts for the diversity of earthquake light sightings. The challenge lies in the phenomenon's rarity and unpredictability, making controlled observations difficult. Yet, advances in seismology, atmospheric science, and high-speed imaging are bringing us closer to answers. Despite their elusiveness, earthquake lights exhibit intriguing patterns. They are more commonly reported in specific geological settings, such as areas with rift zones or active fault lines, like the San Andreas Fault or the North Anatolian Fault. They often appear before, during, or shortly after seismic events, sometimes as precursors to major quakes. For example, during the 2007 Pisco earthquake in Peru, fishermen reported glowing skies moments before the ground shook. The lights themselves vary widely in appearance. Some resemble lightning bolts, others glowing orbs or diffuse clouds. Colors range from white and blue to red and green, with durations from fleeting flashes to sustained glows lasting several seconds. Their altitude also varies. Some hug the ground near fault lines, while others appear high in the sky, suggesting atmospheric interactions. Modern technology has been a game changer. Smartphones and security cameras have captured EQL in real time, providing valuable data. The 2017 Mexico City earthquake, for instance, produced viral videos of blue and white flashes illuminating the night sky, perfectly synchronized with seismic activity. These recordings have helped scientists pinpoint the timing and location of EQL, offering clues to their origins. Earthquake lights have long held cultural significance. In ancient Japan, they were called dragon lights, believed to be manifestations of divine spirits. In Native American folklore, they were omens of change or warnings from the earth. Today, they inspire awe and curiosity, bridging science and wonder. Beyond their beauty, EQL could have practical implications. If scientists can link them to specific seismic processes, they might serve as early warning signals for earthquakes, potentially saving lives. Current research is promising. The U.S. Geological Survey and international teams are studying EQL through interdisciplinary approaches, combining seismology, atmospheric physics, and materials science. Projects like the QuakeLight Initiative aim to compile global databases of EQL sightings, correlating them with geological and atmospheric data. Machine learning is also being used to analyze patterns in video footage, helping identify conditions that trigger these lights. Skeptics remain, and for good reason. Many reported EQL sightings can be explained by mundane causes, power line failures, transformer explosions, or even psychological effects under stress. Distinguishing true EQL from these alternatives is a major hurdle. Additionally, the lack of consistent, reproducible data fuels doubt. Some argue that EQL are too rare to warrant significant research, while others see their rarity as a reason to investigate further, given their potential to unlock new insights into geophysics. The quest to understand earthquake lightning is far from over. Advances in sensor technology, such as high-resolution electromagnetic detectors and satellite imaging, could capture EQL in unprecedented detail. Collaborative efforts between geologists, atmospheric scientists, and physicists are essential to unraveling this mystery. If EQL are indeed tied to precursory seismic signals, they could revolutionize earthquake prediction, a holy grail of seismology. Earthquake lightning remains one of nature's most ethereal enigmas, a fleeting dance of light born from the Earth's restless movements. Its beauty captivates the imagination, while its mystery challenges our scientific understanding. As we continue to chase these elusive glows, we are reminded of the planet's untamed power and the wonders still waiting to be uncovered. Whether a spark of stressed rock or a flicker of atmospheric magic, earthquake lightning invites us to look up, wonder, and keep searching for answers in the interplay of earth and sky.